Hello students, good morning all of you. Now we will discuss important concepts, that is a differential operator. It helps us to take derivatives in case of vectors. It is represented as del. This is also known as del operator. Now the first differential operator is gradient. So we will start from gradient. And it converts a scalar field to vector field with the operation of with the del operation. So in gradient we convert a scalar field to vector field. How it is possible? We will consider any scalar field V. It is equipotential surface. Regarding that, we can say the gradient of V is perpendicular to the surface. Perpendicular to the surface. Now let's try to find something regarding this. Take the change in V, another equipotential surface, V plus del V. Consider one point P here, and you are making change in P in this potential and coming at this level. This is named as Q. The change in length is dl. Consider another point Q dash, length is dash. Consider this Q double dash and length is L double dash. Consider this condition. Now try to find change in potential with respect to change in length. So change in potential, or you can say increase in potential, is dV. For this case, change in length is dl. Now for another case, change in potential is dV and length is dl dash. In case third, the change in potential is this and length is this. Okay, and one thing that you know, that if L is less than L dash is L dash, then dV over dl will be greater than dV over dl dash, then dV over dl double dash. In this way, what we can observe? We can conclude that perpendicular distance is minimum, and in that case a rate of change of V maximizes. So we can write this: the perpendicular distance maximizes the change. Perpendicular distance maximizes the change. Thus, and we know that del V is perpendicular to the surface. On the basis of that, we can say perpendicular distance maximizes the change, and according to that, del V represents the maximum rate of change. The maximum rate of change. And del is represented as del over del x a cap x plus del over del y a cap y plus del over del z a cap z. Del can be represented like that. And if we have to find the gradient of v, then it will be del over del x v in the direction of a x, del over del y v a cap y plus del over del z v a cap z. So del v can be represented like that. For example, v is you can say x, y, z in a scalar quantity, and you have to find the gradient of v. In that case, you will do v ax, y v ay, v az, and for that partial derivative of v with respect to x will give you yz ax xy ay xz ay xy az. This is del v. So this is an example to make this scalar quantity a vector quantity by operating with the del operator. Now if we want to find the directional derivative, then in case of directional derivative, take the derivative in any direction and take the component of gradient in that respective direction. For example, if we have to find the directional derivative of this in the direction of ay, then what we will do? We will do del v dot ay. This is the directional derivative of this in the direction of ay. In the direction of ay. So in the exam, if it is asked that find the derivative in the direction of this or this or this, then just you have to find the gradient of the quantity, scalar quantity, and take the dot product with that direction in which you want to find the derivative. So in this way, so finally in gradient we can say that it represents the direction of maximum change as it is perpendicular to the surface, and the perpendicular we came to know this is minimum, so it maximizes the change. In this way, they represents the direction of maximum rate of change. Second thing, it is represented by del V. Third thing, it is operated for scalar quantity and transform into vector quantity, and it is represented by this. So these few terms that should be clear from here. Now we will take the example to find the derivative in any particular direction, and for that purpose the example is written here. That is, find the directional derivative of quantity V, that is given here, at point P in the direction towards point Q. So there is 2 point P with coordinate 3, -3 and -3, and Q is here with coordinate 4, -1 and -1. We have to find the derivative in this direction. So this direction can be written as APQ, you can say like that, and we have to find the direction, derivative of directional derivative of this in this direction. So what we can write, just we discussed that for that purpose we have to get the gradient of the quantity and we have to multiply the dot product in that direction. So for that purpose we can say del V dot PQ vector divided by PQ with magnitude. It will be unit vector in that direction. So it can be further written as del over del X V, that is X, Y, Z, in the direction of AX, plus del over del Y X, Y, Z in the direction AY, plus del over del Z X, Y, Z in the direction AZ, and the dot product of this with PQ. PQ is nothing, Q minus P. So Q minus P can be written as, PQ can be written as Q minus P. So 4 minus 3 in the direction of, you can say, AX, minus 1 minus 3 plus minus 1 minus minus 3 plus 3 in the direction of AY, plus minus 1 minus minus 3 in the direction of AZ, and it will be PQ. So in this way, if we try to find this, then we can say it YZ in the direction AX, XZ in the direction AY, plus XY in the direction AZ. This is at point P. So we have to put the coordinate X, Y, Z, 3, minus 3 and minus 3. And dot product, we will do P minus Q here. So it will be AX plus 2AY for this, plus 2AZ. And the magnitude of this, that is PQ, will be under root 1 square plus under root 2 square plus under root 2 square, that will be under root 9. So simplify this, it will be 3 minus 3 and minus 3, 9ax plus at p, we have to find at p, so we will put the coordinate of p in this 3 and minus 3, so it will be minus 9 plus 3 and minus 3, so it will be minus 9 az with multiplication dot product ax plus 2ay plus 2az divided by 3. Multiply this. ax will give you 1 and remaining multiplication with ax will be 0. So ax and ax dot ax will be 1, 9 by 3. For this one, multiplication dot product with y will give you the value, remainings will be 0. So 2ay, 2 multiplication with minus 9, it will be 18 divided by 3. And same way, the 18 divided by 3, it will be 3, 6, 6. So it will become minus 9. In this way, we can say directional derivative of v in the direction of PQ is minus 9. Till now we discussed the gradient in Cartesian coordinate system, and we obtained that it was del v over del x in the direction this, y in the direction y, del over del z v az. Now if we have to find the gradient in case of cylindrical and spherical coordinate system, then how we will make our approach, we will learn here. So just relate this from the differential length in case of Cartesian coordinate system, that is change in the length in the direction of x, dy and dz. Relate this with this one, and what we find, del over this quantity, del over this quantity, the coefficient of this, del over this quantity, the coefficient of this. So the coefficient that is with the unit vector will come in the denominator. We can observe something like that. So try to follow this in case of cylindrical and spherical coordinate system. Following that, in cylindrical coordinate system, okay, change the color. In cylindrical coordinate system, write the dl first. It was d rho in the direction of rho plus rho d phi, if I am right, a phi plus dz az. Okay. Now we have to find the gradient of v in cylindrical coordinate system. Then what we will do, del v will be gradient of v will be del v over del rho, because here the coordinates are x, y, z, so we are taking partial derivative with respect to x, y, z. Here coordinates are rho, phi, z, so we will take the derivative with respect to phi, rho, phi, z in the direction of rho plus del v over rho d phi in the direction a phi plus del v over del z in the direction az. We can write like that. Okay. In case of spherical, similarly we will write in that case spherical coordinate. First write dl, that will be just recall dr in the direction of ar and r d theta, and it was r sin theta d phi in the direction of a phi. Yes, this was dl. Now we have to find the gradient. Then what we will do, del over del r this plus in denominator it will be like del theta v plus del v over r sin theta del phi in the direction of. In this way we can find the gradient in case of Cartesian, cylindrical and spherical coordinate system just by taking the coefficient of unit vectors in the denominator in different cases. For example, if we are taking in case of spherical, then the coefficient of AR will be in the denominator, coefficient of A theta will be R d theta, that will be in the denominator, and coefficient of this, that is this, will be in the denominator. So in any coordinate system we can find the gradient. Now take an example in a spherical coordinate system. Example is consider any quantity v to r square sin theta, and the point is radius is to 30 degree, 45 degree. So now we have to find the gradient of this at this point. So first thing that should be clear that this is a spherical coordinate system that is reflected from r theta phi, and another thing, it should be clear that this is theta and this is phi, that is followed throughout the study. So keep in mind, this is theta, this is phi. Theta is the angle from z axis to the point. This is the angle, that is phi is the angle in xy plane measured from x axis. So in this way, this becomes clear that it is a spherical coordinate system. Now to find the del operation, to find the gradient, the first thing that should be clear to know the differential length in that coordinate system. So differential length in a spherical coordinate system, write first, that is dr r d theta, I am writing from here, and r sin theta d phi a phi cap. So this is the differential length in that. And if we know the differential length in any coordinate system, then the gradient of the v is very simple to find. Just del over del r v in the direction of this, just I am writing this again. In the denominator it will be this coefficient, that is this coefficient will be in the denominator with this in the direction theta, plus del over this will be in the coefficient, that will be r sin theta del phi v a phi, and we can simplify this. Del v will be equal to the derivative of v with respect to r, partial derivative. So it will be 4r sin theta ar plus 1 by r, partial derivative of v with respect to d theta. So r and this r will be cancelled out, 2r cos theta a theta plus partial derivative with respect to phi, so it will be 0 since there is no phi. And after that just put the value and find the final result. It will be 4 r is 2 sin theta, theta is how much here? 30, sin 30 is half in the direction ar, plus 2 r is 2 cos 30 is root 3 by 2 into phi. So this is the value. Cancel out 4ar plus 2 root 3 a theta. This is the gradient of v. So in any coordinate system we can find the gradient just if you by knowing the differential. So this quantity, if transformed into vector quantity at this point, then we can say this vector will give the maximum rate of change at this point. That is it for today, and at the next turn we will discuss about divergence, curl and Laplacian. Thank you very much.